if
Yes,
like
please.
if a question asks like how does like write two equations where they give you a salt and they're like write two equations where the salt acts like a buffer, for example. I write the salt dissociating and then I write um, the like at the what's it called? For example, we have ethanoic acid
Hmm.
or sodium ethanoate. I write
Hmm.
sodium ethanoate dissociates into sodium and the ethanoate ion, and then the second equation would be the ethanoate reacting with like
Okay, now let's go through some more examples of the KSP. So this was the equation over here. This is a question. Calculate the solubility of lead to chloride if 25 cm³ of saturated solution contains this much gram dissolved in it. There is a slight mistake in this question. It was supposed to be written as calculate the solubility product. The question is about to find the solubility product, KSP. So you have to find the KSP value. You can also do this correction in at your side as well. Now, this is the volume provided and this is the mass provided. Now, we know that the equation of KSP gives the amount of the concentration in moles per dm cube. But in our question, we are provided in cm cube and gram. That means this value must be converted into the mole per dm cube. For this purpose, we will go through two steps. The first step says that if you have this much mass, it's just simple ratio 0.11035 gram in 25 cm cube. But you are supposed to find the mass in the in the 1000 cm cube. That is equivalent to dm cube. So this time it will become x. So x will then be 0.11035 times 1000 divided by 25. That's the same expression here. So they calculated the amount in terms of dm cube. Now you have been provided the value in gram per dm cube. The next part is that you have to convert this gram into mole. That's simple. Formula of mass over mr is used here. The mass is 4.114, 4.414, and the mr value will be used from the periodic table. Just use the value from the periodic table and it will come out to be 278.2. So divided by 278.2. So this is the value in mole per dm cube. Now this value belongs to the solubility value. This is the solubility value. And we were supposed to find the KSP value. So again, the equation will be converted into the expression. So we have one mole of the lead ion and we have 2 moles of the chloride ions. So over here you have this form. Now I can simply write in the other way that if it is S and this is 2S, then I will put these S and 2S in the equation. So it will become S into 2S with square. Not like this. 2S whole square. S into 2S whole square. Now doing further calculation, it will give you 4S cube. Now KSP is equal to 4S cube. Now you have to find the S value from here. So S will become Ksp divided by 4 and cube root.
Don't we have S?
Sorry?
Don't we have S?
Oh, yes, we have as we have to find Ksp. Yeah,
KSP.
my mistake. We have to find Ksp exactly. So 4 into S value is 0.0159 and its cube. So if you have calculator with you, you can try to solve it. 4s cube, Ksp is equal to 4s cube, or it's equal to 0.0159 with power 3
1.6.
into 4.
Yeah, basically, if you round it, you get 1.6. But this one, they got like. Oh, wait, the chlorine has a different value.
Don't look at the below, look at this value. This is the answer.
Oh, okay.
This is the answer.
Okay, never mind. Yeah.
So it should give you, if you round off the value, it should give you 1.6 into 10 raised to power minus 5. Is this what you're getting in the calculator?
Yeah.
So this is how you can simply do this. Instead of going through all these multiple steps, you can simply use these steps to find the answer. And this is what already mentioned here. If we go back to the question, this one, they use this method over here, 4x cubed. So it's up to you. You can write the letter S or you can write the letter X. It's up to you. Okay, so I think that's clear with respect to such type of the questions, right? Yani, is it clear to you now?
Yeah, yeah.
Okay, so we can now move on to the next topic. The next topic is predicting precipitation. Now, precipitation, as you must be familiar, that shows how they are the precipitates present within the solution. Have you already seen the precipitates whenever you have performed experiments in the lab? Did you see the precipitates?
Yeah.
Okay. Now, this KSP can help you to find whether there will be precipitate form in the solution or not. By precipitate, we mean, I can simply write here, by precipitate we mean that there should be the formation of the solid in the solution. Since precipitate is a solid form, so there should be formation of the solid of the ionic compound which we are considering. We say that Ksp indicates for a easy term, I will write that if it is the AB ionic compound, that is a sparingly soluble compound, it shows equilibrium with its ions. So if it is plus ion and B is a negative ion, Ksp indicates that we have the equilibrium between its solid form and its aqueous ion. There is an equilibrium between these two. What if we have the more amount of the ions present? Let me do one more correction here.
No
The
precipitate.
AB, sorry,
You were saying if we had like more ions,
yeah,
then probably
I'm,
not
I'm
be.
I'm writing it as AQ, and this is also AQ. What if we have more amount of these ions, either A positive ion or the B positive ions? It would shift the equilibrium towards the left side. Is that so?
Yeah.
So according to Lee-Chatterjee's principle, if we increase the amount of the A negative ion and B negative ion, it will move the equilibrium, or it will shift the equilibrium towards the left side. That means you will get more amount of the solid. In other words, the AB compound will start settling down in the solution as precipitates. So we are considering the value of the product of A positive, concentration of the A positive with the concentration of the B negative. So if the concentration of these two values is greater than the value of the KSP, KSP is when we have the equilibrium state, but this is considered to be non-equilibrium state. KSP was applied when we had the equilibrium state, but if we add by ourselves, if we add any particular value of the A positive ion or the B negative ion into the solution, then it should become non-equilibrium state. So if the value becomes greater than the value of the KSP, then this would give you precipitate. So precipitate will form in this situation. Is this clear up to this point?
Yeah.
Now we can use a different letter for this situation. The multiplication of A positive ion multiplied with the B negative ion is considered as capital Q in the non-equilibrium state. But if it is an equilibrium state, then you use the KSP constant. Then this is the symbol for the equilibrium state, and for the non-equilibrium state, it's a Q symbol. So we take an example here, barium carbonate. Barium carbonate dissociates into barium ions and carbonate ions. Now, according to the KSP value, it's 5.5 into 10 to the power minus 10. But if the concentration of this product gets greater than this value, then precipitate will form. On the other hand, if the product of this, if the value of this product gets less than the KSP value, then no precipitate will form. If no precipitate is formed, that means barium carbonate, can further dissolve. It has not reached to the level of precipitation. That means we can add more amount of the barium carbonate into the solution. Is this clear?
Yeah.
So remember that solubility product is only relevant for salts which are sparingly, very slightly soluble. The concept cannot be used for soluble salts such as sodium chloride. Remember that soluble salts include salts of group 1 elements, all nitrates, ammonium salts, and many sulfates. Halides are generally soluble except for lead-2 halides and silver halides. So basically, we have to understand that which type of the salts are there which can be dissolved in water. All the nitrates can be dissolved, all the ammonium salts can be dissolved, all the group 1 element salts can be dissolved. These are all the soluble. But those which are not all, but we can say most of them are soluble. These include the sulfates, and then among the halides, only these two examples are examples of insoluble. The rest are all soluble. We have taken these values from the O level and A level, AS. This whole information is coming from both the levels, AS and O level. But anyways, within the question, you'll be able to identify, or the question will already indicate whether the compound is sparingly soluble or not. But if they ask you to compare with any other compound, then definitely you will be required to use your prior knowledge, the prior knowledge of the AS and that of the O level. Okay, now the same topic from the other source book. The solubility product can be used to predict whether precipitate will form when two solutions are mixed. So if the concentration values are not in equilibrium, then in that case you use a letter Q, capital Q. So we compare Q versus KSP. Q is basically the amount of the product of ions in non-equilibrium state. So if the Q value is greater, we said that the product will precipitate. If the value is greater than the KSP value, then precipitate. That means the solution is supposed to be saturated. We call such a solution as supersaturated. And on the other extreme, if the value is less than KSP, then such a solution is said to be unsaturated and that more ionic solid could dissolve. So this is the two different cases. And then with respect to the situation and they are equal, then definitely it is at equilibrium state and solution is saturated. So you have to learn the type of the solution as well: supersaturated, saturated, and unsaturated. So up to this point, we have just learned that whether the compound would precipitate on the basis of its value when compared with KSP value. Is that clear?
Yeah.
Now the next topic is common ion effect. Common ion effect is also related with the KSP and Q. So common ion effect will use these two concepts alongside. Common ion effect means you will have a solution of sparingly soluble compound and you will add some more ions into the same solution that will be common to the sparingly soluble compound. So what we learned from the previous topic that if the product of the either A ion or the B ion, if you increase whether the value of A, that will also increase the value of the Q, or if you increase the value of B, that will also increase the value of Q. So you can basically add any one of these two ions into the solution of the sparingly soluble compound. If you have a sparingly soluble compound AB and then you additionally add another compound, let's suppose I write that compound as CB. You are adding externally another compound that contains the same B ion. So what will happen? The concentration of this B negative will increase. Isn't so?
Sir, can you repeat?
Okay. I was saying we have AB as the sparingly soluble compound. We have AB as the sparingly soluble compound which dissociates into the A positive ion and B negative ion. Now, if you want to increase the value of any one of these two, you can simply add another compound. I'm adding a compound CB. This another ionic compound contains similar ion of B as that in the AB. All right.
Yeah.
I'm adding CB. If I have a beaker in which there is a solution of AB already present, then I will add some more. I will add some amount of CB into this compound, CB. So what I will have? I will have more amount of the B negative ion because of this additional CB, right?
Yeah.
So if the value of the B negative ion will increase, that would mean it will not remain in KSP anymore. The KSP state will be violated, it will then have value greater than the KSP. The value of this product will then be higher than the value of the KSP, and that will lead to the formation of the precipitate. Is this clear?
Yeah, I got it.
Now, this is what we learned in common ion effect. In common ion effect, the solubility of the dissolved salt is reduced. The solubility of the dissolved salt is reduced by adding a solution of a compound that has an ion in common with the dissolved salt. This is the definition of the common ion effect. You have to learn this definition. Common ion effect says that you will reduce the solubility of the dissolved salt by adding another solution of a compound which has the ion in common with the dissolved salt. So I had previously compound AB, and I reduced its solubility by adding another compound containing B as a common ion. So we went back to the topic of previous topic where we said that if you increase the value of any one ion, it will lead to the unequilibrium state, and so that compound will then be insoluble, or it will be called as precipitate. We'll now take an example here. The example will help you. We have AgCl as sparingly soluble compound, and it dissociates into Ag ion and the chloride ion. Now, if you try to increase the value of either chloride ion or a silver ion, whether silver ion or chloride ion, what will happen? It will move back to the AgCl state, and AgCl will then be precipitated out, right?
Yeah.
Now, how can you increase the value of one of these two ions? You can take the example of the sodium chloride, NaCl. NaCl is a very much soluble compound. It's a very soluble compound, and it dissociates into complete sodium ions and chloride ions. So just by adding sodium chloride into this AgCl, the amount of the chloride ion will increase. You could say increase over here or increase over here whatsoever, but there's an increase in the chloride ion. So by increasing the value of the chloride ion, the equilibrium will shift towards the left side, and it will then be precipitated. So precipitate of the AgCl will be obtained. So how would you got the AgCl precipitate? By adding the sodium chloride. So by adding sodium chloride, you reduce the solubility of the AgCl. By adding NaCl, you have reduced the solubility of the AgCl because chloride ion was common ion over here. And this is called the common ion effect. Is this clear now?
Yeah.
So chloride ion is a common to both sodium chloride and silver chloride. The added chloride ions shift the position of the equilibrium to the left, and so sodium chloride is precipitated. The addition of the common ion, which is the chloride ion, has reduced the solubility of the silver chloride because its solubility product has been exceeded. Solubility product has been exceeded means the value has exceeded the value of the KSP. It has increased beyond the value of the KSP. So when the product of the concentration of the Ag ion and chloride ion, this is written in terms of equation, you should remember, this means when the product or the concentration of these two ions is greater than the KSP value for silver chloride, a precipitate will form. This is what we learned in the previous topic. The solubility of the ionic compound in aqueous solution containing a common ion is less than its solubility in water. Okay. The solubility of ionic compound aqueous solution containing common ion is less. So whenever we add common ion compound into the previous compound, so its solubility decreases. They are saying that if you do not add any compound, then it will simply be of water. But if you add aqueous solution of the same common ion, then definitely solubility will be decreased. In simple, if either there is an excess amount of the cation ions or there are excess amount of the anion ions, the solubility of the salt will decrease, and this is called the common ion effect. This definition is not giving you clear idea, so I would better suggest you to learn these two lines as a correct definition. This is just the idea of the common ion. It is not a proper definition. Common ion effect from the third resource book you have, as I said, as I told you, I'm using these three resources. So in the third source book, what you see again a complete uh, explanation of this common ion effect. If we add soluble sodium chloride to the solution of this one, the concentration of the chloride ions increase. So NaCl will convert into sodium ion and chloride ion. So that means the amount of this chloride ion has overall increased. So when it has increased, it will definitely shift towards the back side. For the AgCl, it cannot move to the back side of the NaCl. It cannot move for NaCl because it's already in the forward direction. It does not have any equilibrium sign. So that's why it cannot move to the back side. So when it moves to the back side, it will form the AgCl again. That means the solubility of the AgCl has been decreased and you are getting the precipitate out of it. This is known as common effect. If a solution containing a common ion is added to sparingly soluble solid at equilibrium, it will become less soluble. This is the overall summary. If a solution containing any common ions is added to a sparingly soluble solid at equilibrium, it will become less soluble. Over here, we are only considering the chloride ions. What if we add any such salt in which there is a higher value of the silver ion? This will give you the same result. If you, by adding any compound containing the same silver ions, it will also lead to the uh, formation of precipitates of AgCl. I can say silver nitrate. Let's suppose we say that all the nitrates are soluble. They are very much soluble. So when this will be added into the water, it shall form Ag ions and nitrate ions. So we will now have common ion as the silver ion. In this case, the Ag plus will be the common ion. So when silver ions will be increased, it will shift the equilibrium towards the left side and AgCl will be precipitated. In performing calculation with the common ion effect, we assume that the concentration of the common ions is equal to the concentration of the most soluble substances. So since common ion must be there, that common ion comes from the most soluble substance. Uh, in in the in this example, the most soluble substance is the NaCl. So NaCl is providing the most common ion as the chloride ion. Or if you take this example, then AgNO3 is the most soluble substance. This concentration will be far greater than the concentration of the sparingly soluble substance. Now, there is a question on this common ion. I will try my best to explain you in better way. We have equal volumes of the 0.05 mole per dm cube lead bromide and lead nitrate, and they are mixed together. Determine the minimum concentration of the lead nitrate needed for a precipitate of lead bromide to form. Ksp for the lead bromide is 7.9 into 10 to the minus 5 mole per dm cube. So basically, we have two in a compound. We have the Pb, Br2, this one, and we have the lead nitrate. They are these two ions over here. Now, as a result of these two compounds, the Pb ion will be the common ion. This will be the common ion in this case, and the sparingly soluble compound among these two, do you know which will be the sparingly soluble compound between lead bromide and lead nitrate?
Oh, it's lead bromide. Lead bromide, yeah.
It is the lead bromide. It cannot be lead nitrate because we know all the salts of nitrates are soluble. So this is the sparingly soluble. Okay. Now we will find the concentration of the lead nitrate in overall, that is the 0.05 mole per dm cube, because this is the value for both this compound and this compound. Both have the same value. So if we apply this value on the lead nitrate, it means that you have 0.05 mole per dm cube of the lead ions and also 0.05 mole per dm cube of the nitrate ions with 2 moles. But if you check this value for the lead bromide, then lead bromide is basically a sparingly soluble compound. That means the value for this case, it will be written as this: lead ion plus 2 moles of the bromide ions. Now, if you want to find how much value is there of the bromide ions, then you should understand this 0.05 mole was there for 2 moles of the bromide ion. That means for 1 mole of the bromide ion, the value will become 0.05 divided by 2. This is the value for the moles of the bromide ion coming from the PbBr2. And we need this value because in our question we have to find the product. So the solubility of the lead is calculated from this information, that it is a very much soluble compound. That means PbNO3 twice will have the same value for lead and same value for the lead, but we need the value of only lead from here. But for the value of bromide, we are considering the other salt, that is lead bromide compound. Okay, we have now found the values. The value of the bromide ion will come out to be 0.025. This is equal to 0.025. So you need this value and you need the value of lead from here. So one value is taken from here for the bromide and one value is taken from here. Now you put these values into the equation, that Ksp is equal to, Q is equal to lead ion into bromide ions. You are using this equation. It is the non-equilibrium state. It is a non-equilibrium state, not the equilibrium. So non-equilibrium state will give you this value. Now for precipitation to occur, because it asks you to determine the minimum concentration of lead nitrate for a precipitate or lead bromide to form. So if you want to find the amount at which lead bromide will precipitate, that means we will first check the comparison of these two values, or sorry, we find out the value of the solubility value. The solubility value for the lead ion, because we are supposed to determine the minimum concentration of lead nitrate needed. Lead nitrate needed means you have the value of the lead over here, because It's a very soluble compound, so you are finding the value of the lead here. That will be considered as S. S is calculated, that is equivalent to 0.0126 mole per dm cube. This is the value of the S over here. However, the equation should be written like this. The value of the lead is already there. Pb into, for bromide, there were 2 moles. So we already divided the value by half. When we divided the value by half, we are only getting 0.025 with a scare on it. There is not 2s. It's not written like 2s scare. It's not like this because we have already divided the value over here at this point. We divided the value by 2. That's why it's written like this. So so this is the equation. From here, the value of the lead ions are calculated. That is now equal to 0.01264 mole per dm cube. So this is the concentration of the lead bromide needs to be in the solution. So concentration of just our 0.01264 times 2 needs to be added. So I'm not getting this point, what they are trying to say over here, but what we can say that if the value exceeds this value, then PbBr2 will precipitate. That's what I know. If you increase the value above this value, then PbBr2 will precipitate out. You can watch this recording in detail so that you can understand this question. There is just one single numerical on this topic in the literature. Otherwise, the questions of the topicals are much easier compared to this explanation. Is that clear?
Yeah.
All right. Now, this is our final topic of this chapter, which is the partition coefficient, Kpc. So partition coefficient Kpc, that's a comparatively easier topic than the previous one. So we understand that there are some compounds which can dissolve in more than one solvent. For example, you know that we have water as the solvent. We can have chloroform. We can have the other types, ammonia as a solvent. We have the hexane as the solvent. These are the different names of the solvents, and they are used to dissolve the solute in them. So basically, if you select two solvents, which are not soluble into each other, if I select water and another solvent as hexane, it's a totally non-polar compound, that is C6H12. C6H12 and this is water. They are not able to dissolve into each other. So this is one solvent, this is the second solvent. And now I have to select a solute. I will select any particular solute which can be dissolved in water and which can be dissolved in hexane. Solute is dissolved in both water and hexane, but these two solvents are not soluble into each other. So such a combination must be selected, and from there we will study the partition coefficient. So what partition coefficient says, it is again an equilibrium state, and this equilibrium state says that if we have such a solute which can be dissolved in solvent 1 as well as solvent 2, but the two solvents are not soluble into each other, then what will happen? You will find two separate layers. We have separate layer for one solvent and a separate layer of this other solvent, and the solute, it is already dissolved in both the solvents. It is dissolved in the upper layer, it is dissolved in the lower layer. So if you consider this example, in this example, we have the ammonia as the solute. The ammonia is considered as the solute, and the solvents, there are two solvents here. We have the organic solvent, and this is one solvent, and water is the second solvent. The second solvent is the first solvent, let's suppose. So ammonia can be dissolved in the organic solvent, ammonia can be dissolved in the water. When it dissolves in water, we write AQ. That's the solution of ammonia in water. But for organic solvent, you just write ammonia present in the organic solvent. Is this clear to this point?
Yeah.
So for this type of the equilibrium, we can write the constant, the Kpc constant that says product divided by reactant. Now in this case, solvent 2 is the product, solvent 1 is the reactant. So concentration of the product divided by concentration of the reactant. Now what these concentrations are? These concentrations are basically the concentration of the solute in solvent. This is not just one thing, there are just two things here. The solute dissolved in solvent 2 divided by solute dissolved in solvent 1. That's what it means here. So you will have such type of the expression x in solvent 2. This x, for this case, x is considered to be solute here. They have designated x as the solute. So x in solvent 2 divided by x in solvent 1, and they are taken in the square bracket. That means the concentration are in mole per dm cube. So this is how we write the expression for the Kpc. Just like all the other constants, this also depends upon the temperature. So if you change the temperature, then the value of the Kpc will change. The other conditions for the solvents are the solvent must not react with each other, and the solution need to be fairly dilute. The solvents 1 and 2, they should be inert towards each other. They should not react with each other. And they are also considered to be very much dilute. What about the solute? The solute must be in the same physical state and same chemical form in the two solvents. So it should not be different one in solute, in solvent 1 or solvent 2. It should not be different. It should remain in same physical state and same chemical formula. Because this is a simple ratio, they are not units of the partition coefficient. So yes, it's a ratio, so no units are there. Now from the other source book, partition coefficient, as I explained that the ammonia is taken as this solute here, and this ammonia is being dissolved between the two solvents. One is the organic solvent, other is the water. So basically it is considered that for equilibrium expression, or sorry, for a chemical equation, you should always consider the aqueous form is written on the left side and the organic side is written on the product side. In all the cases, you will have these two combinations, aqueous and organic. Aqueous is every case, it's a water, but organic is not fixed. It can be hexane, C6H12, it can be hexane, it can be CCl4, it can be any other organic compound, but that compound should be considered. Okay, let me tell you two combinations here. You will have combinations of the solvent in this way. If you will be provided water as first solvent, then in its opposite, you will always have the organic solvent. There will always organic solvent in opposite to water. But if you are provided organic solvent instead of the water, it would be a polar compound on the left side, and opposite to this, there will always be a non-polar solvent on the other side. So this is the combination. Either you will have water versus organic solvent, or you will have the organic polar, or maybe it is not organic, it's just polar. That means it could not be an organic compound, it could not be a water, but that will definitely be a polar solvent. And opposite to that, you will always have a non-polar solvent. Is this clear to you?
Yeah.
So if we consider this example, then ammonia is the solute, whereas the solvent are organic solvent versus water. And if we take another example here, now in this case we have iodine as the solute, I2 is the solute, and then solvents. The solvent in this case will be hexane. It's hexane over here, and it's water over here. So I2 is dissolved between hexane and water. Now we can see the color of iodine in solid form is gray, and you can find they are settled down, which means the rest of the excess amount of iodine is insoluble, but the remaining one which has been dissolved is represented in these two colors. We can see that although hexane is basically colorless, but you can see it's purple over here. What does it indicate? It indicates that iodine has been dissolved in the hexane solvent, and that's why you see this violet or purple color. This purple color is basically when iodine is dissolved in the hexane. Otherwise, hexane itself is a colorless compound. And in the water state, you can see it's yellowish or sorry, it's light yellow. So this light yellow color is indicating that some amount of the iodine also dissolved in the water. Now for this type of the equation, you have to construct the Kpc, Kpc expression, the partition coefficient expression. So it is always said to be that the water will come in the numerator, and the organic state will be mentioned in the, my mistake, water is in the denominator. There is some problem with this page not writing.
Is water always in the denominator?
Yes, water will always be in denominator.
Okay.
That's a rule. Let this page refresh. So water is always in the denominator like this, and the organic phase will always be in numerator. This is organic phase. In other cases, if there is no water, then it will be the polar solvent. In the denominator, there will be a polar solvent, and in the numerator, there will be a non-polar solvent. So how would you know whether it's a non-polar? How would you know it's a polar? Here come your knowledge of AS level. You will use your knowledge of the AS to identify the polarity of the compound. So you know all those compounds which have greater electronegative difference in their molecules, they are polar, and those which are non-polar, you know that you can have CCl4 compounds are non-polar. So you will be using your knowledge of the AS to predict the nature of the compound, the nature of the solvent. Is that clear?
Yeah.
There is now a picture over here to tell how the effect. So I think we should continue from this page onwards in our next class, and we'll discuss the action of the partition coefficient in detail.
Okay. Thank you, sir. Bye.
Welcome. Bye bye. Take care.